So today we're going to be talking about stormwater runoff. All right, so the idea is, where does stormwater go? What does site development have to do with this? What does it mean for a watershed characteristic? Stormwater management, how that's done. And then the calculation, the analysis comes into when we're using, there's lots of different methods to use. One of the simplest and easiest is the rational method. And then we're going to talk about storm characteristics. We're not going to really go over an example. I'll show you some, some explanation with the example. We're not going to go into a ton of example. And then we're going to talk about how you reduce stormwater runoff. All right. So where does stormwater go? So you can kind of see that, precipitation hits the ground. And once it hits the ground, the runoff can go into little streams, which then go into larger streams, a river, and out to like the ocean. It can also go down through the soil. All right. So it's either absorbed by the ground or the vegetation. It's runoff, meaning into streams and rivers that eventually go out to some kind of waterway, street, and then it's drained from the site to some other place. All right. It can be also detained on site, meaning kept on site. So that last idea, the runoff onto your neighbor's property, that's one of the big issues, is that if you discharge onto your neighbor's property, it can cause a lot of damage to your neighbor's property. And so there's lots of laws and reasons why you can't just discharge it anywhere, or you discharge into a river. A lot of sediment or chemicals, if you're on a farm, can go there. So that's why a lot of times you want to reduce runoff, either keeping on site or improving or increasing the amount that's absorbed. The way you do that is using detention ponds or retention ponds, or you can use underground storage. So site development, a lot of times when you develop a site, it's either it's untouched land that you're developing, or it's already developed land that you're redeveloping. So anytime you change a site, whether it's improvements or changes to the site, that's called site development. Whether you put in buildings, pavement, landscaping, grading. The thing is, though, typically when you develop a site, a lot of times it's a new site. Anytime you do that, you're putting in more hard surface than you are the absorbent surface. So if anytime you're putting in pavement or a building, there's no longer the open grassy area or open forested area or just open land area to absorb it. So you're reducing the amount of usually reducing the amount where water can be absorbed. We're trying to reverse that. So a lot of new development, if you're changing an previously developed site, you can increase absorption by changing the type of asphalt that's used, or increasing the amount of planted area, or doing things differently, not paving over everything the way we have done in the past. So typically development increases runoff and decreases absorption, and that increases stormwater runoff. We're trying to reverse that. So regulations have evolved in order to protect the environment, protect water quality, reduce sedimentation, meaning the removal of sediment and soil, protect property, reduce site runoff, reduce impact on storm drainage systems. So like a lot of flooding happens because we've damaged so much natural systems. You look in a lot of coastal areas, they've killed wetlands and reduced marsh areas, which have always been natural buffers. So you get storm surge from hurricanes and other storms, where you get more increased runoff from storms. We're getting larger and more intense storms. And all of this just kind of goes hand in hand with the issues that we're encountering. So watershed characteristics that affect runoff. So if you have more intense rain, you have more runoff, right? You have more water being introduced to the system in a shorter amount of time. So, if it's a slow, steady rain, a lot of that rain can just be absorbed immediately into the ground. But if it's a very, very intense period of rain in a short amount of time, the water can't absorb that quickly. So as we said, rainfall intensity, you got a lot more rain in a short amount of time. That will increase runoff. Soil type, so certain soils absorb more water than other soils. So if you had a lot of sandy soil without a lot of fine material, so without a lot of silt and clay, it will absorb a lot of water, sand and gravel. But if you have a soil with a lot of silt and clay, that's a lot of very fine material that will not absorb a lot of water very quickly. The slope and topography. So if you have steeper slopes, you'll have more runoff. Whereas if you have flatter land, it will, the water will not travel as quickly, so it will tend to absorb more. The soil compactedness, so very compact soil will not absorb a lot of water, whereas loose soil, like farm that's just been tilled or something like that, or your yard, if you just kind of dug it up a little bit, will absorb a lot more water. Vegetation, if it's more heavily vegetated, so grassland or a wooded area, a forest area, will absorb a lot more than a non-vegetated area. So, as we said, there's a lot of regulations and laws that dictate how runoff, pre-development and post-development runoff can work. The idea is that you want to calculate the impact of the development on the stormwater runoff, meaning you calculate before you've touched the site what you expect the runoff to be for a certain type of storm, and then you calculate for after development and compare the two. In general, if there's a change in runoff, any increase needs to be kept on site in such a way that it rediverted into a stormwater system at a slow rate so that the stormwater system doesn't get overwhelmed and flooded. So the whole idea is to come up with a stormwater management plan. The way in which you determine the pre-development runoff and the post-development runoff is this idea called the rational method. The rational method, it's a formula where Q equals C times I times A, where Q is the runoff, the quantity of runoff measured in cubic feet per second, so cubic feet of water per second. C, I is the rainfall intensity, so you usually say it's a half inch per hour, inch per hour. Those are like some pretty hefty rainfall totals, but how much water is falling every hour. Area is measured in acres, so we're going to need to figure out acres. And then runoff coefficient, it's just a number that's been associated with certain types of landscape or surface. So whether it's grass, asphalt, a roof on a building, a forest, and then also it has to do with the slope. So if it's a grassy area that's very flat, it's one number. If it's a grassy area that's a really steep slope, that's another area. So it's a big chart full of numbers, and you just kind of look it up. All right. There's a slight adjustment that we're going to be using. So we're going to introduce this other coefficient, C sub F. So the Q, CIA are the same, but C sub F is an adjustment factor that has to do with how often the storm is that we are going to be designing for. So we're going to use the 50-year storm, 100-year storm, 500-year storm. So what these all mean is a storm that is supposed to come once every 100 years. Are we designing for that storm, or are we designing for one that's supposed to come once every 25 years? Something that's been happening is, with the climate change that we've been experiencing, people are realizing that these storms that are quote unquote 500-year storms or 1,000-year storms are not nearly the 500 or 1,000-year storms that we anticipated. They're showing up more and more often. So a lot of our data is based on only a very short snippet of time, relatively speaking, 50 years, 60 years, 70 years worth of data, which, if you think about it, it's a lot of time in, our lifetime. But, when you're talking about, rainfall data, if you're trying to estimate a 100-year storm, and you don't even have 100 years worth of data, or a 500-year storm, and you don't even have 500 years worth of data, it's a lot of estimations, and sometimes they're right, sometimes they're wrong, and we're realizing that they're more often wrong than right. So this C sub F, that circle's a little off. It's all about the return period. So if we're designing for a 1, 5, or 2, 5, 10 year storm, it's just a coefficient of 1. But if you're designing for a 100-year storm, it's a 1.25. So you're increasing the amount of runoff because, a 100-year storm, it shows up less frequently because it's more intense. You don't have the super intense storms every year. So you're designing for the one that that one intense storm that shows up once every 100 years, and you can go higher than 100 if you really want to. So storm characteristics, the duration, so how long a storm lasts for, whether it's something that lasts for a half hour, for a full day, for multiple days, how many inches of rainfall, and so the intensity is the depth, the amount of rain divided by how long it happens. So the design storm, again, is this like a critical piece of infrastructure that you don't ever want to get flooded, or is it something that residential houses, unfortunately, very few people live in a single house. If it's a full neighborhood, it's a different thing. But if it's a single house, you're not going to design for a 500-year storm for a house. You're going to design for a storm that happens every so often. A lot of these design storms are dictated by local regulations. So if you live in an area where flooding is an issue, you have probably much more strict and stringent local regulations. Whereas if you live in an area where there's very few flooding issues, then probably not as much. The design storm is always described as the return period. So it's a 5-year, 10-year, 100-year storm, as well as the duration. Is it 24 hours? Is it the 100-year storm that lasts for 24 hours? It's a pretty intense storm. So there we go. And all of this is described in maps. So you see this map here on the right-hand side. You have these contours that go across, and it's kind of hard to see, but those contours indicate rain level amounts. So the intensity is the design storm can be found from maps and charts. We're going to be using these charts that come from NOAA, National Oceanic and Atmospheric Administration. They have these charts for lots of places around the country. And so the way you read this chart, if you look at the top, you have 1, 2, 5, 10, 25, 50, 100, 200, 500, 1,000. Those are the recurrence intervals. So a lot of times we're going to be looking for the 100-year 24-hour storm or 100-year 1-hour storm. That's what is located here. So you have 60 minutes on the left-hand side. That's a storm that lasts for 1 hour, and it's expected to happen once every 100 years. So once every 100 years, you're expected to get a storm that produces about 3.12 inches of rain in that 1 hour in Nashville, Tennessee. All right. And then you use that as your design number. There's all kinds of other stuff for, how these numbers are generated. So there's an example here. We're going to actually go through a set of calculations like this, but the whole idea is that you look at the pre-development stuff. So you have a 3-acre site. It's originally a farm, and then you want to put on a 30,000 square foot asphalt parking lot. You want it to be, you want to reduce or limit the amount of runoff, and your design storm is a 25-year 1-hour rainfall. So the whole point is that you do a pre-development analysis, come up with, I'm just going to kind of run through this kind of quickly. You do a pre-development analysis, all this stuff. Oops. And so pre-development, you're expecting that the maximum stormwater discharge is 1.5 cubic feet per second from the site. All right. And then you do a post-analysis. So you a lot of numbers stay the same, but you have different areas now. And just kind of running through, you have the post-analysis, meaning that you have 3 cubic feet per second. All right. So if you before development you had 1.5 cubic feet per second. After development you had 3 cubic feet per second. So the change was 1.5 cubic feet per second. So you need to do something with that extra water that's running off the site. That's why you need to look at alternatives like, okay, instead of regular pavement, there's something called permeable pavement where water can run through it. You can introduce more vegetation. You can do a rooftop garden. You can put in rain barrels. You can do lots of other stuff. Most often, what you would do, if you want to do LEED, which is like an environmental friendly certification, lots of plantings, lots of vegetation, permeable pavement, rain gardens, cisterns, you can like your whole parking lot. You could actually like dig it out, put in like a big like pool underneath almost, and then cap it over with the pavement. That's a very expensive system, but that's a way to do it. Or you just have these big trenches. You see them all over the place. These big trenches out in front of buildings, kind of between a parking lot and the road, or something like that. They're called swales or detention ponds. A lot of developments have them now. All right, so that's the basics of of stormwater management, and from here on, we're going to be going over practice calculations for how you do pre-development, post-development analysis.